Hi everyone. So in this video we'll provide the analysis. We'll start providing analysis in this video and the coming two videos and then interpret this analysis of early stopping. And this analysis is very similar to what we have done with L2 regularization, and it will give us an insight on how to compare early stopping to L2 regularization and what's the analogy between them, and that will as we do that, that will show us actually in a very rigorous way the advantages of early stopping. So let's follow the same principles that we have done while analyzing L2 regularization. So assume there is no bias terms. We are ignoring the effect of bias terms in the network. And we approximate the cost function by a quadratic approximation or through the truncation of the Taylor series up to the second order derivative term or the Hessian in the neighborhood of the optimal value omega star of the unregularized cost. So omega star is the optimal of the optimal parameter setting of the unregularized cost. We approximate the cost function by quadratic approximation around omega star. So j hat of theta will be equal to the cost, the unregularized cost, omega star, plus sorry, the gradient. There is a first order derivative term that will be equal to 0 because omega star is the optimal. So the gradient of j with respect to omega at omega star is equal to 0. And then the second order derivative term is given by half omega minus omega star transpose times the Hessian. So this is the Hessian of the cost with respect to omega evaluated at omega star times omega minus omega star. Now when you take the gradient of this, then it basically, the gradient with respect to omega, j of omega star is a constant, right? It doesn't depend on omega. So it just becomes h of omega minus omega star. And this is similar. So these steps are the same as what we have done with L2 regularization. So this is unregularized. This is just the impact of this approximation, quadratic approximation. Now let's analyze early stopping. So let's say we start with parameters initialized to 0. So omega 0 at time step 0, right? So this is the time step index, right? Equal to 0. And then omega tau at time step tau, right? So this is the step index, right? So equal omega tau minus 1 minus epsilon, and epsilon is the learning rate, right? Times the gradient of the cost with respect to omega and the cost evaluated at the parameter setting obtained in the last time step, right? So for time step tau, it's the last time step minus the learning rate times the gradient evaluated at that last time step, right? So this is equal omega tau minus 1 minus epsilon h omega tau minus 1 minus omega star, right? So I replaced in the calculation of the gradient here omega by omega tau minus 1, right? So now very simple transformation. So let's add minus omega star to both sides. So omega of tau minus omega star equal I minus epsilon h omega tau minus 1 minus omega star. And I here is the identity because this term becomes omega tau minus 1 minus omega star, and this is the same epsilon h omega tau minus 1 minus omega star. Now because omega star is the minimum, so h is positive semi-definite. And we discussed that before, right? So it's the minimum of the unregularized cost. H is the Hessian of the unregularized cost with respect to omega, evaluated at omega star. So all the second derivatives will point upwards in all directions, basically, and that's what it means that h is positive semi-definite, right? Because this is a minimum, so the first derivative is increasing in all directions. So now omega of tau minus omega star, so now I can decompose h, since it's positive semi-definite, into q, which is a matrix of the orthonormal eigenvectors of the Hessian, and lambda, which is a diagonal matrix of eigenvalues of h, right? So lambda is a diagonal matrix. And then q transpose, right? So I could do this transformation to h. Now again, let's right to the, let's multiply to the left of both sides by Q transpose. So on the left hand side, I have Q transpose omega of tau minus omega star. And on the right hand side, I multiply Q transpose by I. So this is the first term, right? And then in the second term, because Q is an orthonormal matrix, so Q transpose Q is just the identity. So when I multiply that second term by Q transpose from the left, I just get epsilon lambda Q transpose, right? So I end up with I minus epsilon lambda Q transpose times omega of tau minus 1 minus omega star, right? So basically, this is the difference from the optimal of the unregularized coast, right? So at time step tau, the difference of the parameter setting from the parameter setting of the unregularized optimal when projected on the orthonormal matrix of eigenvectors of the Hessian evaluated at omega star, this thing is basically I minus epsilon lambda times the projection of the difference of the last time step, right? So here, this is omega of tau minus 1 minus omega star. So this is the difference of parameters of the parameter setting from the unregularized optimal in the last time step projected on the eigenvectors of the Hessian. And this is the same thing at the current time step. So in every time step, I multiply the same thing by I minus epsilon lambda, right? So if I start by omega 0 equals 0, then that term, if tau equal 1, that term will be minus omega star, right? So I will start by minus Q transpose omega star times I minus epsilon lambda. And then that becomes Q transpose times omega 1 minus omega star. Now when tau equal 2, then I multiply the same thing, which was, remember, minus Q transpose omega star times I minus epsilon lambda. I multiply it again by I minus epsilon lambda, right? So in the tau time step, I'm getting I minus epsilon lambda to the tau, right? So basically, Q transpose omega of tau minus omega star, and here we put it on the other side, the Q transpose omega star. This thing equal, so we put here the, so if you take the identity times Q transpose omega star and put it to the other side, it becomes Q transpose omega of tau minus omega star. That thing becomes minus Q transpose omega star times I minus epsilon lambda to the tau. Right? Now, if I minus epsilon lambda to the tau, remember, is what? Lambda is diagonal, I is diagonal. So this is a diagonal matrix of 1 minus epsilon lambda I in the ith diagonal element, right? Raised to the tau. So if 1 minus lambda epsilon I, the absolute value of it is less than 1, right? Then what happens? Then what happens is that if I compare with L2 regularization, so this is from the last time we discussed this approximation with L2 regularization. Remember we said omega tilde, the solution you obtain with L2 regularization, equals Q transpose omega star, projecting omega star on the orthonormal matrix of eigenvectors of H, and then you project back at the end by this Q here. And then in the middle, you scale by lambda over lambda plus alpha, right? So lambda I over lambda I plus alpha, because this is all diagonal. So so this matrix is a diagonal matrix with elements lambda I over lambda I plus alpha, right? So what you get here, if I put Q transpose in both sides, then I have Q transpose omega tilde, Q transpose Q is I. So I end up with this. And I could rewrite this as I minus lambda plus alpha I inverse times alpha times Q transpose omega star. Right? So what I get here, right, is basically there is an analogy between early stopping and L2 regularization. They become equal if I minus epsilon lambda to the tau equal lambda plus alpha I inverse times alpha, right? Now the next video will be on interpreting this. So this gives us a relationship between tau, epsilon, and alpha. Remember, epsilon is the learning rate, tau is the number of time steps for early stopping, alpha is the L2 regularization coefficient. So here we can get an interpretation of early stopping as some kind of L2 regularization with a specific choice of alpha that corresponds to the number of time steps that early stopping stops after. Right? Thank you.